Chapter 11 deals with optimization problems with two or more choice variables. So consider an optimization problem of this type. Let our dependent variable now be z. Z is a function of x and y. Now, there are two choice variables, x and y. And suppose that this is a maximization problem. So what you want to do is choose the values of x and y so that you get the maximum value of z. Your first order conditions for this type of problem are very simple. It's just partial z partial x equals 0. The partial derivative of z with respect to x equals 0. And the partial derivative of z with respect to y equals 0. In fact, these are the first order conditions for either a maximum or a minimum. They're the same. And actually, the intuition behind this is really clear. Suppose you're at a point, x0, y0. And at this point, you evaluate partial z, partial x. You evaluate partial z, partial y. Suppose partial z, partial x does not equal 0. At this point, suppose partial z, partial x does not equal 0. Oh, to take the easy case, the easiest case perhaps, suppose partial z, partial x is positive. At this point, x0, y0. Why does this point, x0, y0, not give you a maximum? How do you know that you can't be at the maximum value of z if partial z, partial x is positive? It's easy. Just think about it. What does it mean if partial z, partial x is positive? Just what does that mean? Andra? Yes, okay. So, and in simple words, just in simple words, what does it mean? If partial z, partial x is positive, what does that mean in simple words? Okay, so if you increase x a little bit beyond x of 0, what happens to z? It increases. So you couldn't possibly be at the maximum value z because all you have to do is increase x a little bit and z will get bigger. At the maximum, partial z, partial x can't be positive because that means all you have to do is increase x a little bit and z will get higher. Okay. So suppose partial z, partial x is negative. Why does that mean you cannot be at the maximum value of z? Well, if partial z, partial x is negative, what does that mean in simple words? Exactly. It means x and z move in the opposite direction. So all you have to do is decrease x a little bit, and z will get bigger. So we ruled out partial z, partial x being positive. And we also ruled out partial z, partial x being negative. What's left? Partial z, partial x equals 0. Okay. So similar reasoning will show you that partial z, partial y must also be 0. If partial z, partial y is positive, all you have to do is increase y a little bit and z will get bigger. If partial z, partial y is negative, all you have to do is reduce y and z will get bigger. So That's just the intuitive explanation for these first order conditions. These conditions must be satisfied as long as your function is everywhere differentiable, as long as these derivatives exist everywhere. Then you have to be satisfying these first order conditions. Okay. Let me give you, I wish I had more time. It seems like we always don't have enough time in this course. I wish I could explain the second order conditions to you, but there's not enough time. What I'm going to do is simply state the second order conditions for a maximum and a minimum. If you have enough time, read through chapter 11, and it explains in detail where these second order conditions come from. But I'm just going to state them. All right, let's look at both a maximum and a minimum. The first order conditions are, as I said before, partial z, partial x, and let me just shorten this by writing this partial z, partial x equals partial z, partial y equals 0. Same thing for the minimum. The sufficient conditions, or the second order conditions, the second order sufficient conditions, for a maximum there are two parts. The second derivative of z with respect to x has to be negative. The second derivative of z with respect to y has to be negative. And if you multiply these second derivatives times each other, they have to be greater than the cross partial derivative, partial z, partial x, partial y squared. Okay. The product of these two second derivatives has to be greater than the cross partial derivative squared. Okay. For a minimum, these two have to be positive. And this same condition down here has to hold. This part is the same for both the minimum and the maximum. Okay.